Hi everyone, welcome to this supplementary video. And in this video, we will be basically discussing about drag on a projectile. Um, and this is something you may have done in your freshman physics courses, but if not, I just want to remind you a little bit about this problem. Is that when you tangentially throw, let's say, a ball or some other object at an angle with the ground. So let's say you are actually holding this in a ground. It could be like a football or like a baseball that you are throwing at an angle. It'll take some sort of trajectory and then it'll hit the ground. And this is known as a projectile motion. So initially there is essentially velocity that you give u naught at some angle theta with the ground. So there is some u naught cos theta, u naught sine theta. And the basic idea here is that you can essentially trace a trajectory under the assumption that the gravity is happening in the y direction. This is just the convention that I have taken. And you can essentially like write the equations and you can do the trajectory. It's very simple. It comes out to be a parabolic trajectory profile. You may have heard that, at 45 degrees, it's the maximum range that you can get and so on. So the question is, all of that is done while assuming that there is no drag or that the air is not having any effect on this throw. So now what we really want to do is to be able to kind of also take into account the drag part of it. So this is a little bit more complex than some of the things we have done in the class, and I just want to mention a few things. So imagine that we are at some particular velocity, and I want to purposefully use a different symbol here, just to be kind of like u bar. Okay, this is just to kind of say, and this is not near the ground. This is at a general position. So let's imagine that it threw some sort of like you threw it something like this. Then in that case, the drag would be sort of parallel to this u bar, right? And but in the opposite direction to the u bar. Then we'll have some sort of gravity forces here, some buoyancy forces to the top. We can ignore buoyancy forces in terms of when it's in air, though you can add it, it's pretty easy, and we'll discuss this. So this is the free body diagram. In general, when we were doing this for something like, a vertical system, the direction of the velocity was much simpler. But here, the essentially the velocity can be composed in du and v. So this is the horizontal direction, small u, horizontal direction. This is the vertical direction. Okay. And so the point being that now I will have components of the drag, which will be essentially, I have to take in vertical and horizontal direction. I would note that we'll assume Reynolds number to be large for sphere. So we'll assume CD to be 0.445. So that's just an assumption. And this is generally true for like, real life objects. For very small objects is where when you go, or when you are using very like viscous liquids, you'll go small Reynolds number. So this is for a sphere and the diameter of the sphere is D, just to clarify that as well. Okay, and the simple rho S and rho comma mu as usual. We can also take that. Okay. All right. So now the question is, how do we proceed from here? So we'll do force balance, but now we will do in two components. So first from this, we know the magnitude of the force is going to be by rho u square by 2 into pi d square by 4 is equal to CD. So from here you get CD is equal to, and I'll be careful here. I'll write rho u bar square by 4. Okay, so u bar is the full velocity. Rho u square bar is equal to 2. So we get CD. FD is equal to CD times rho u bar square pi d square by 8. Okay, so note that this is based on the magnitude of the velocity, but here there are two components, and that's why you have to be a bit careful. So u bar square, or if I write in terms of components, I can also say CD into rho of u square plus v square. Okay, pi d square by 8. This is what we get as our force. Okay. Now I have to take the component of this force. So if I take the component of this force in the horizontal direction, so remember I will basically take the u part of it, and the net part will be u square plus v square square root in terms of magnitude. And the direction is the opposite. So let's just do this in a second. So in the horizontal direction, there is no buoyancy, there is no gravity. So horizontal direction, I simply get some sort of FD. I'll just write it as X. Okay, FDX. So FDX, now this is the part where trigonometry can help, and if you're not comfortable, we'll discuss this. Pi d square by 8. What I'm doing here, I'll say u and by square root of u square plus v square, and then I'll take a negative sign because it's opposite to u. Okay, opposite to u, which makes sense. It's the opposite to velocity. So this gives me FDX is equal to minus CD into rho into pi d square by 8 into square root of u square plus v square times u. Okay. Now in vertical direction and in horizontal direction, essentially what we're saying is m du by dt. M du by dt is equal to f dx, which is already in the negative direction. So if I take the magnitude, I can just simply say, actually, let's do that. Might be easier to take the sign directly at the last stage. Let's say minus f dx here. So we just say opposite to u in the denominator. So the f dx was the magnitude, okay? Opposite to u. So here, if you simplify this, this we have done. So this is rho s into pi d cube by 6. This implies that du by dt comes out to be minus 3 by 4 into rho by rho s times b into u square plus v square times u. Okay. This is essentially your du by dt. Okay, this is in the x direction because you're doing the x balance. So the rate of change of the velocity should be u. Now we will also do the y balance. And so in the y balance, we have the gravity. So we have the gravity, we have the buoyancy, which is rho times pi d cube by 6 times g. And then I have the, so depends on the sign of the velocity, but in this case, it's going upwards. I'll just write it like this for the simplicity. And fdy. And if the velocity is going down, it should reverse, which we will discuss in a second. But for simplicity, we can just ignore this, ignore in air. Okay. And so now we say m dv by dt, so this is vertical direction. Vertical direction. So again, we say the m dv by dt, both the values are negative right now. M dv by dt is equal to minus mg. And then this is the component. Okay. And instead of u, I will take the v by square root of u square plus v square. So minus cd into rho into u square plus v square into pi d square by 8 into v by square root of u square plus v square. Okay. Now note one thing, when we do the projectile, the velocity sometimes also goes down, right? In that case, it automatically CD becomes positive. So the drag force is proportional to V in this case. So it automatically switches the sign, which is good. But just to be sometimes you have to be careful with this. Or this, when you write again, simplify this, it's very similar to the other one, just that there is also gravity. P by 4 rho CD by rho S times D into U square plus V square square root times V. So these are the two equations that I get. Obviously, they are more messy. Both of them have U and V with them, but they are those equations. And you finally can say dx by dt is equal to U. the acceleration in the the rate of change of distance is speed, and then dy by dt is equal to v. So you have to solve these four equations to finally find a trajectory of a projectile. Okay. But if you do that, you should be able to kind of solve the problem. So just to again summarize what we have been discussing, and I'll then show a quick code which does this. Um, so we have discussed how a projectile is done. Then we calculate the drag force. The main key part here, which was different than something we have done in the class, is that the drag force happens opposite to the direction of the velocity. But here the velocity is neither horizontal nor vertical. So you have to take components. To take components, you essentially take the components of the u and divide by the magnitude to kind of get the right component of that, which is what we did here. To get in the x direction. So x direction is only deceleration, and decelerates because of drag. Note that if CD is equal to 0, there is no deceleration in the u direction, just keeps going. Similarly, we have in the v direction, we have gravity, but then we also have the same drag correction. And see, this is very similar to your class. Here you just had a u square and a u square in the x direction. Here you just get u squared plus v squared times u because you're taking a component. So that's the slight difference, but in direction. So with these four equations, these are numerical. So initially we can say at x is equal to 0, y equal to 0, like basically it's at some sort of origin. Then, u of 0 equal to u naught cos theta. Some value we give and the projection angle, and v naught equal to 0 is equal to v naught sine theta. So this is how you can think about it. And so we do this and we can sort of solve this. So this is a little quick, but hopefully you got the sense. So in the what I will do is I will now show you that these four equations, and I'll show you a MATLAB code which does this for us. And so let's quickly see that MATLAB code. And let's do this. So we go here. Actually, let me just share the full screen to avoid any. Yes, so here we are. So this is the MATLAB code. Let me maybe increase the size here to make it easy to see. Right. So here essentially it's like a 5 centimeters in diameter, which is like about a couple inches, I guess. So that's fine. Then some sort of 8,000. This is high. You can reduce this like a steel ball or something like that. Or like some sort of metallic, but you can do few thousands or something like that. Then right now this is in water, so I'm throwing this in water, but let's just do like 1. So 1 kg per meter cube. Then we have u naught is equal to 10 meter per second. So initially we throw for 10 meter per second. Then the angle initially, let's start at 5/4. Drag coefficient is 4.445, gravity is meter per second square. Right now time is 10, we can change it if we need to. And so the main thing happens here. So this is essentially saying we have dx by dt, dy by dt, du by dt, dv by dt. So we have four equations: dx by dt, dy by dt, dv by dt, du by dt. And that's basically what you see here. So dx by dt, dy by dt, dv by dt, and du by dt. And this 1, 2, 3, 4 are essentially the way MATLAB does it. Don't confuse this y1, y2. This is more MATLAB's notation. But this equation is saying dx by dt is equal to u. This equation is saying dy by dt is equal to v. This equation is saying du by dt is equal to minus 0.75 into cd into this times this velocity magnitude times u. And here you have added gravity, and then instead of velocity u, we have velocity v here. So these are the same equations I've called up in MATLAB. If you're interested, I encourage you to learn about these things. And so here, basically, we can run this code. And what I've done is I've taken one case where we have a drag. In the other case, we have no drag. And like in a sense, the drag coefficient is set to be 0, but the same equation. And so we'll see what happens when we run this. So run this code. And in this case, you can see that the drag is it's affecting it very little, right? So the drag is so little in this case that you can almost overlay on top of each other. By the way, the blue ones are the ones with the marker size of almost marker size, sorry, the blue ones are the one with the drag and the red ones. So they're almost completely on top of each other. So now let's change this and say this was water, right? Okay. And if you generally add water, you should add a little bit of correction because of buoyancy. We have just not done it, but it's a very simple correction. It won't change much and everything else remains the same. So we do that and then we expect the drag to increase, right? If you throw something in water, and as you can see, now there is a very big sort of correction here which comes because of water. So it very quickly sort of falls off here in this projectile. This is a 45-degree projectile, as you can see nicely here. The red curve remains the same for both sort of air and water, but the blue curve drastically changes because now there will be much more drag in water. We can do something else. You can see we're throwing something much bigger. I don't want to go maybe 0.5 meters is okay. So 0.5 meters is about 1.5, 1.5 feet. So it's a big object, let's say like some big spherical, and you're throwing in air. So let's do still air. And then let's see if it shows some effect here. Still not much. So air drag is still, as you can see, pretty small right now, and that we don't really see much of the drag. Perhaps if we go up higher in the velocity, we might start to see something because when you increase the velocity, you can technically increase the drag. So we haven't gone that far because this is still 2 meters per second, 2 seconds. So maybe if you go 20 seconds, maybe we'll see something interesting. Yeah. So now you can see some sort of deviation starts to come. There is some sort of falling off here when you really throw something very fast. And now imagine when you're sending spaceships or shows the velocity is extremely high. So if you go 1,000 meters per second, and then you may have to go longer, let's say 200 seconds just to show you. Then you can start to see now there's a very clear gap that starts to come in. And there's even in air, you start to see that difference coming up. So, just to play around with it, it's cool to see that. For simplicity, let's go back to the water case, couple of inches in diameter, and this is, let's say, 1,000. Just to remind you, we have this what happened here. Also, the velocities was also, I think, 10. That was the problem. So now we see the same case. So velocity is 10, and then we are able to kind of discard this projectile. But now maybe let's also, just for kind of nice visualization, we should add another angle. Okay, so we have not changed the angle yet. So if we make it, let's say, pi by 3, and let's make I hope I didn't close the first one. So it actually plots on top of the other. Yeah, so let's do that. And so I've made the angle pi by 3. So now, as you can see, this is a good example. And so the square, so the squares here, this one line here is the 60-degree angle, and this is the 45-degree angle. And so this is a nice sort of, you can see this is a square one. So this also does go further. 45-degree does go further even within drag. But I believe actually the optimum is something other than 45 with including drag. I don't remember the angle. It might depend on the drag coefficient and so on. But as you can see, there is more complexity than I like this. So I think this is very instructive, nice to code it up and also sort of observe. We'll put this code on Canvas as usual. But if there are any questions, feel free to reach out. And I hope this video was useful. All right, bye-bye.